Hello everyone, this is Chandana. In this video, we are going to discuss the design of Dynamic DDR4 Memory Controller with intelligent refreshing and parallelism. Our main aim in this project is to create a memory controller based on DDR4 with intelligent refreshing and parallelizing SDRAM refreshes with access capabilities that adapt dynamically depending on instruction locality. Providing high-speed memory access is essential for most modern and high-performance computing systems, and the increase in memory-bound applications further aggravates this. At the lowest level in memory hierarchy, high-speed access can be facilitated by using dynamic random access memory. DRAM is abbreviated as dynamic random access memory, which was patented in 1968 by Dennard. This is significantly cheaper than SRAM, which is static random access memory with one transistor and one capacitor, and a bit is represented by a high or low charge on the capacitor and is significantly slower than SRAM. In 2000, JDEC released a double data rate specification in which data was transferred on both the rising edge and also the falling edge of the clock. The second generation of DDR memory, that is DDR2, scales to higher clock frequencies. And DDR3 was first introduced in 2007, whose power consumption is 30% less than DDR2, whereas DDR4 is more efficient than DDR3. The table shown here compares different types of dynamic random access memory in terms of their speed, bandwidth, and packaging standards in which they are available and advantages of DRAM DDR4 over the other types of DRAM. If we see the different generations of dynamic RAM, in each generation we will find improvement in speed and reduction in power consumption, and each generation is more sophisticated and detailed than the last, necessitating a control mechanism to efficiently monitor and control the DRAM memory. This is where the need for a memory controller arises. Memory controller is an important part of the computer system that controls the memory and is responsible for data exchange between the memory and the CPU. The memory controller determines the maximum memory capacity that the computer system can use, the number of memory banks, memory type and speed, memory particle data depth and data width, and other important parameters. Having a memory controller significantly reduces the area and complexity of CPU while promoting more flexibility and adaptability to different DDR specifications. Memory operates on a frequency defined in the DDR specification on which it was based and is different from the processors in its operating speed. The memory controller serves as a bridge between the CPU and the memory, allowing for the safe transaction of data. Further, the expanding and volatile nature of memory as newer generations are introduced and more innovations are made demands a more sophisticated control mechanism that can be fulfilled using the memory controller. A memory controller also ensures that all specifications laid out for that memory generation are met perfectly. It also ensures that all address translations from logical address to physical addresses in the DRAM are abstracted away from the CPU, significantly improving CPU performance. Ultimately, having separate logic for memory control allows for cheap hardware as integrating all memory control functions into CPU would require replacing the CPU every time the newly defined specification can no longer be supported by the integrated chip. For all these reasons, we need to implement a memory controller for our computing devices. Let us have a look at the modern memory controller. A modern memory controller acts as an interface between CPU and the memory, abstracting away the details of DRAM operation from the processors. To do this, a memory controller needs to ensure that the following functions are implemented. It needs to ensure that all timing and refreshing constraints are satisfied to ensure safe data storage. It needs to implement row buffer management policies which work with other features such as command scheduling to optimize the performance. It also needs to enable logical to physical address translations to take commands from the CPU and read or write to different parts of the memory, while also allowing for address mapping schemes to facilitate storage optimization in the DRAM through features like dynamic index tables. But there are some issues with the memory controller as well. The memory controller is responsible for request scheduling and memory mapping from logical to physical addresses, along with ensuring that the physical device timing and power requirement are being met, ensuring sufficient DRAM refreshes. However, these DRAM refreshes, if implemented conventionally, interfere with the request accesses and significantly increase access latency. Further, naive memory mapping approaches lead to inefficient use of available space in memory, such that the memory cannot hold data continuously due to fragmented available spaces in the memory. There have been efforts to resolve these issues in the research being conducted. Here are some approaches. The first one is Predator, a predictable SDRAM memory controller. This memory controller provides a guaranteed minimum bandwidth and maximum latency bound to the intellectual property. This is accomplished by using a novel two-step approach to predictable STRAM sharing. The first approach is done by defining memory access groups corresponding to the pre-computed sequences of STRAM commands with known efficiency and latency. The second approach is done by using a predictable arbiter to schedule these groups dynamically at runtime such that an allocated bandwidth and a maximum latency bound are guaranteed to the IPs. The second type of memory controller is RAIDR, Retention Aware Intelligent DRAM Refresh. It is a low cost mechanism that can identify and skip unnecessary refreshes using knowledge of cell retention times. The key idea in this is to group DRAM rows into retention time bins and apply a different refresh rate to each bin. As a result, rows containing leaky cells are refreshed as frequently as normal, while the most rows are refreshed less frequently. Radar requires no modification to the DRAM and minimal modification to the memory controller. The third type of memory controller is DAP, Dynamic Access Refresh Parallelization. This approach addresses the drawbacks of a per bank refresh by building more efficient techniques to parallelize refreshes and access within the DRAM. Instead of issuing per bank refreshes in round robin order, DAP issues per bank refreshes to idle banks in an out of order manner. Furthermore, DAP proactively schedules refreshes during intervals when a batch of writes is draining to DRAM. These issues have been tackled by refreshers introducing novel controllers, but most of them have been targeted in their approach. We aim to combine the key strategies used in these controllers to develop a unique and effective memory controller. This is the outline of memory controller that we have proposed and implemented successfully. While we aim at achieving parallelization in memory access with refreshers to reduce refresh interference on demand requests and have dynamic memory mapping in DRAM for uniform memory utilization. Below are the mechanisms that we have implemented in our project. The former is to enable parallelization between refreshes and write requests across different banks by overlapping refresh and write latency, while the latter is to implement an intelligent memory mapping scheme with DRAM utilization optimization. This improves the system performance and energy efficiency for a wide variety of different workloads and DRAM densities.
Hi, Avish here. As we saw in the previous slides, a modern memory controller needs various features to be considered a good DRAM memory management system. Some of the key features which are implemented in our design have been listed here. We start with the open page policy, which ensures proper row buffer management, followed by optimized command scheduling, which schedules memory requests depending on row access by commands. Then we have dynamic refresh parallelization, which allows for DRAM refresh policies to be defined and improves the performance through latency overlapping. And finally, we have DRAM memory mapping, which intelligently stores data in the DRAM by considering data size and available space in the DRAM. Now let's talk about open page policy. Open page policy is a row buffer management policy that helps improve the performance of the memory by exploiting request locality. In this policy, when a row is accessed, the row buffer is kept open and not closed until after the request is complete. The row buffer is only closed whenever we encounter a row conflict. That is, the data we are looking for is not in that row. In this way, we can work in tandem with command scheduling to ensure requests accessing the same row have efficient access to the row. Open page policies attempt to gather multiple requests into each row buffer access by speculatively delaying the pre-charge operation to execute additional row reads. This enables latency, scheduling, and power improvements possible with page mode accesses. These policies can cause issues when applied to the numerous request streams of a many core systems, as priority is given to accesses to already open pages, introducing memory request priority inversion and leading to potential starvation issues. Next, we have a look at how command scheduling is implemented. A command scheduler finds the optimal order of servicing for the incoming request to the DRAM. Command scheduling is very important as it significantly reduces DRAM access time. Command schedulers usually separate read and write commands into separate queues, giving priority to read commands over write commands, and usually divide instructions into per bank queues, allowing for easy operation reordering in the same bank. Some of the common policies for scheduling are FCFS and FRFCFS, or first come first serve and first ready first come first serve. In first come first serve, the oldest command is serviced first, whereas in first ready first come first serve policy, we build on this by laying down two requirements for the commands to be serviced. First, the request with the row hits are serviced, followed by requests which are the oldest. This helps us exploit row buffer locality, working in tandem with the open page policy for reduced access time. In our project, we implemented FRFCFS strategy by queuing commands into bank-wise read and write buffers and reordering to exploit row buffer locality. Command schedulers are not easy to implement as they need to ensure timing constraints are being met along with simultaneous tracking of resources such as data buses, address buses, row buffers, etc. for queue requests while also needing to do DRAM refresh. Next, we'll look at DARP or Dynamic Access Refresh Parallelization. So, this is a new per bank refreshing scheduling policy to proactively schedule refreshes to banks that are idle or that are draining writes. In traditional memory controllers, we use all bank refresh mechanisms where a rank receives a fresh refresh command. It sends the command to a DRAM internal refresh unit that selects which specific banks to refresh. uh, REF command triggers the refresh unit to refresh several rows in every bank for a period called RFC. Because a REF command triggers refreshes on all the banks within a rank, the rank cannot process any memory request during RFC. Modern systems which use this mechanism are very restrictive as they require refreshes to occur in a round robin fashion without flexibility. This is where DARP comes in. It has two components. The first component is a out of order per bank refresh that enables the memory controller to specify a particular bank to be refreshed as opposed to the standard per bank refresh policy that refreshes banks in a strict round robin order. With out of order refresh scheduling, DARP can avoid refreshing active banks with pending memory requests, thereby avoiding the refresh latency for those requests. The second component is a write refresh parallelization that proactively issues per bank refresh to a bank while DRAM is draining write batches to other banks, thereby overlapping refresh latency with write latency. These two schemes help improve the performance of the device. In our design, we implement dynamic access refresh parallelization by developing a DARP module that implements the shown algorithms on the screen and sends bank IDs to be refreshed to the refresh logic in the command scheduler for a DRAM or refresh operation. Finally, we'll have a look at the DRAM memory mapping and how it is implemented. Memory mapping is an integral part of the controller which receives a logical address and then proceeds to give us the physical address where the requested data is stored in the DRAM. The memory mapping decodes the logical memory address of the requesters into a physical SDRAM address consisting of bank, row, and column. An interleaving memory map is used to map the burst of a group to different banks. Depending on the burst size, different parts of the logical address correspond to different parts of the DRAM, such as the rank, bank, row, and column. Further, we use an index table to store data across various banks in the DRAM to boost parallelism. And data is stored dynamically by intelligently detecting available space in the DRAM and finding the smallest space where data can be filled continuously. We implement the memory mapping in our memory controller by using a fixed burst size, which allows us to decode the logical address into the physical address of the data through the index table. With this, we have coded all major functionality needed in the design of a modern memory controller.
Hello everyone, I'm Rajesh. I'll walk you through the implementation strategies and the techniques that we have followed in realizing this project. As Bhavesh has already described about the important scheduling methods and other few features that we have combined together to make this concept a reality. So the implemented features are the open page policy, the optimized command issues system, and the memory mapped indexing table, as also a scheduling algorithm called as DARP. So what are they? The open page policy helps minimize the row misses, while the optimized command issues make sure that the refresh and the write commands are interleaved. A specially developed index table mapping technique inspired by NTFS file system in the actual storage systems is making sure that the CPU requests to the memory commands translations are mapped intelligently to the data necessary in the free spaces and retrieve them whenever required. And DAP allows per bank refreshes and hides the writes in the refresher cycles. So how did we make the system happen in a limited time environment? The first initial proposal. The first proposal states that the system is a state diagram based evaluation, so which is basically a system using the behavioral constructs of the system Verilog and the Verilog to simulate the very functioning of this implemented system. We thought we'll be going with the UVM based suite where we will be simulating RAM functionality as well as the CPU requests, but limited to the timing constraints proposed to use Ramulator by our professor. So we used Ramulator in our next plan. So as the name says, it's a RAM plus simulator. So it is a system used to simulate the RAM, and it's very accurate that it can give you the per time results. Since it really has become the de facto for all the RAM-based research as well as the implementation strategies. This is the overall structure of the design of the Ramulator, the way the system has been built. So this Ramulator can be used in three different modes, where the user would send in the memory traces directly from the CPU, and the system can generate a memory controller as well as the DRAM and would give you the results out of it, or a gem5 based simulator where the gem5 would be acting as a control system, which would issue commands to the Ramulator. Ramulator would simulate the RAM based simulations for it, or a memory trace systems, which would be the direct memory commands coming off of the memory controller. So this way you can simulate your RAM behavior, the device behavior. So what is Ramulator? Ramulator is a publicly available architectural RAM simulator developed by Dr. Onur Mutlu in 2012 at Carnegie University. So the system is a super cycle accurate as it would exactly reduce the ticks in the actual implemented hardware of the system. The simulator is written in C++11 standards, which helps in backward compatible and also make it to be used in the same size cluster for the parallel computations. This simulator proven helpful for both DRAM construction as well as the controller unit designs. Not only DRAM, the system as it is completely modular is be able to simulate various memory devices just by defining the device properties at the build phase of the system. How it is organized. So it is a completely hierarchized and abstracted system. As you can see, it has a main.cpp, processor.cpp, memory.cpp, controller.h, refresh.cpp, scheduler.h, and dram.h. What are these files? These are the files written in C++ in a header as well as in the C++ programs, which basically abstract the system of how the Ramulator system works. So here we are simulating the processor.cpp by just giving the trace space files. The controller.h is basically the controller which controls the system and it translates the CPU request to the memory commands and send it to the memory. And DRAM.h, which is sitting at the end, would act as a DRAM that we are trying to simulate. So how did we evaluate our system? As the Syrian Babesh has told you about the system's construction and the system's feature. So, but we have to be at a phase where we have to make sure that the system is working fine and it is giving the expected results. So the mode which we have given is a CPU-based system, which was a trace-driven. So we just have to give the trace files to the system and it would act as a single core issuing commands to the memory. We have come up with a different configurations of cores, whether it was a high intensive memory loads and the low intensive memory load, which would act as a single core or abstracted as a single application, which is doing the memory commands. Now, we have used a 4 cores as well as 8 cores, which are basically the combinations of this high memory intensive as well as low memory intensive workloads. As the CPU core, as the trace file increases, the number of CPU cores acting on the RAM increases. So how did we construct our RAM? So we defined the RAM in the .config file of the Ramulator. Here we have defined 2 channel RAMs and ranks. We have simulated 2 ranks. These 2 ranks are spread over the 2 channels, and the speed of the RAM is 2400, which is basically 2400 megahertz. And the way this RAM is organized, this is a 8 GB in cross 8. That means 8 chiplets spread across 2 ranks, which constitute of 8 GB. So the outputs are basically the executed instructions, the CPU cycles, IPC, row misses, row hits, row configs, and average access latency, read bandwidth, and write bandwidth. So why did we choose them as our metrics? Because these are the metrics that make a real world scenario. So now these are the results that we have. The base system has used a generic system with a FRCS based scheduling policy, while the proposed system has been modified with 4 proposals which we have put forward in the previous slides. We have highlighted them with a green slide. We can clearly see that row misses has been reduced by at least 1 or 2% in the 4 core based systems. But coming to the 4 core or the 8 core systems with an equal share of high as well as the low workloads, we can see a drastic improvements in our system, as well as the row conflicts, which happen to be very less compared to the base system, and also the row conflicts for the write. And we can see there are zeros for the write conflict. This is how we have scheduled our memory controller to be. When there are a lot of write instructions happening, they buffer up and they are all discharged in the single go. Now, what are the conclusions that we can draw out of it? As you can see the graph on the screen, it is based on the metrics of the system, which would have tend to be at near 0. So as you can say, the lower the graph, the lower the size of the line is, the better the system is. On the orange graph, you can see it is of equal share of high loads as well as the low loads working in 2 on 2. We can see that there's a drastic improvement on the system, which where row misses for the reads have been decreased a lot, up to 20%, and also in the row misses for the writes. So improving the writes is a critical, or I would say the crucial aspect of a memory controller. This memory controller acts because of the row translation system that we have implemented in our controller. The system utilizes a file system based indexing to intelligently store the incoming data into the places which are suitable for the data to be settled at. Continued conclusion, as you can see, these are the metrics which are higher, the better. And as you can always see, the row hits for the reads have been increased drastically. And also the row hits for the writes are also been increased drastically. And executed instructions in the IPC instruction through output have been shot up by half the percentage. So this is a percentage comparison between the base system that we use for the evaluation as well as the proposed system. And this is completely because of the DAP as well as the address mapping tables technique that we have included in our design. And finally, these are the references or the papers that we have referred to for construction design. And this is how we conclude our presentation. Thank you.